Okay, so here's a puzzle that appeared in Mathematical Carnival, a collection of puzzles by Martin Gardner. Okay, so 40 matchsticks are arranged to form the skeleton of an order 4 checkerboard. And the problem is to remove the smallest number of matchsticks that'll break the perimeter of every square. Okay, so here's a picture situation. So we have 40 matchsticks. And here's how to do it in 9 removals. Okay? So you can see that all the 2 by 2 squares are broken, all the 3 by 3 squares are broken, the big 4 by 4 square is broken, and the 1 by 1 squares are broken. Now, is this the smallest? Is this the optimal solution? And it's pretty clear that it is. There are 16 1 by 1 squares. At most, 2 can be broken by a single matchstick removal. You can only break 2 when a matchstick is removed from the interior of the checkerboard. And you also need an extra one to break the outer 4 by 4 board. So you need at least 16 over 2 plus 1, which is 9. So the solution is 9. Okay, so we can easily generalize this to any n by n board. So just applying the exact same argument for n even that we applied in n equals 4, we get this lower bound for the minimum number of matchstick removals, which I call mu of n. And we can get a similar lower bound, which you can see there, for n odd, but that is harder to show, and I won't go into that now. These are Gardner's solutions that solve this problem for n odd and n even. These are optimal, so they obtain the lower bounds that we just saw there. So you can see that this procedure, this is the solution for the 4 by 4 case, and then we tile the board radially, and that's the n equals 6 case, and you can see it's easy to extend to the n equals 8 case, and so on. Okay, so 3 dimensions. This is how we're going to generalize this further. Okay, so matchsticks of length 1 are arranged in the form of an n by n cubical lattice. And we want to remove the smallest number of matchsticks that will break the boundary of every cube. And the boundary in this case is the set of matchsticks that lie on any face of the cube. So if we have a 2 by 2 by 2 cube, that includes the cross matchsticks and the skeleton of the cube. So mu3 of n is the minimum number of matchstick removals that will break every cube in the n by n lattice. All right, so that's a picture of the situation for n equals 2. We can get a very, very similar lower bound now for the 3-dimensional case as we got in the 2-dimensional case. So there are n cubed 1 by 1 by 1 cubes in the n by n lattice. And the removal of a matchstick can break the boundary of at most 4, which is quite easy to see. And you can only break 4 when a matchstick is removed from the interior of the n by n cube. So you get this bound. Mu3 of n is at least n cubed over 4 plus 1. Because you need to remove another one to break the outer n by n cube. Okay, so we're going to describe a procedure now for n even that achieves this lower bound. All right, so I'm just going to talk about tiling for a sec. So in the 2-dimensional solution, we had this domino that tiled the board in an efficient way. And we could remove the center matchsticks of each domino, and that gave us our solution. The analogy for the 3-dimensional case is a 2 by 2 by 1 cuboid. And when we tile our board, our cube, and once we've tiled it with 2 by 2 by 1 cuboids, we remove the matchstick that is common to all 4 1 by 1 by 1 cubes, and that gives us our solution. All right, so this is our procedure. Okay, so we split the n by n cube into n by 2 cuboids. So this is an example for n equals 6, and this works for the n even case, of course. All right, and now for each n by 2 cuboid, we tile it like this with 2 by 2 by 1 dominoes. It might be difficult to differentiate here, actually. But you can see each domino is a different color. So we tile it like this with 2 by 2 by 1 dominoes and remove the center matchstick of each domino. And we're left with a 2 by 2 by 2 cube in the center that is not tiled. Okay, so we do that for each n by 2 cuboid, and we're left with a tower of untiled cubes. So we're left with an untiled 2 by 2 by n tower in the center. And we tile it like this. So we put one here, one here, one here, one here. And we're left with 4 more 1 by 1 by 1 cubes. And we remove 2 more matchsticks to break those, the arrowed ones, as you can see here. Again, this is for the n equals 6 case. And this also breaks the outer cube, as you can clearly see. And this, in fact, does work. It doesn't break all the 2 by 2 by 2 cubes, all the 3 by 3 by 3 cubes. It breaks all the cubes. Okay, let's just count really quickly. This procedure requires the removal of n cubed minus 4 over 4 plus 2, which is n cubed over 4 plus 1 matchsticks. And the reason for this is that we have tiled it by 2 by 2 by 1 cuboids that have 4 1 by 1 by 1 cubes in them. Okay, so therefore we've achieved the lower bound for n even, so mu3 of n is n cubed over 4 plus 1. So, okay, and just some future questions. So some progress has been made on the case where n is odd for the three-dimensional case, and I have this conjecture. For n is congruent to 3 mod 4, mu3 of n is this. And I pose another question, what about n is congruent to 1 mod 4? Another question is, can we generalize this problem to 4 or 5 or higher dimensions? So talk about, say, a 4, n by n by n by n tesseract, and remove the smallest number of matchsticks that will break every tesseract. Okay, thank you very much.